In this highlight video, we will talk about the reduction of carbon-carbon pi bonds. After watching this video, you should be able to describe methods to reduce alkenes to alkanes, including predicting their products and whether there is reaction stereoselectivity. In addition, you should be able to contrast methods to reduce alkynes, including, again, predicting products and the stereochemistry of the products. Alkenes are typically reduced by catalytic hydrogenation. This involves the addition of hydrogen gas to an alkene in the presence of a metal catalyst. This reaction doesn't take place without the catalyst. The catalyst is usually palladium, platinum, or nickel. Oftentimes we'll see palladium adsorbed onto inert solid like charcoal. So often you'll see something like this, palladium on carbon. As an electrophilic addition reaction, a hydrogen will add to each of the carbons of the double bond. We'll add 2 hydrogens. Because both H's add to the same side of the pi bond, this is a syn addition. So what we'll see in the top example 1, we don't really see any stereochemistry. We just go from an alkene to an alkane. Example 2, though, we generate 2 new stereogenic centers, and notice that the 2 hydrogens are on the same side of the ring. Alkynes can be hydrogenated too. Because there are 2 pi bonds, 2 equivalents of hydrogen gas can add. And in fact, the first addition gives us a cis alkene, but we can't stop at that point. That alkene will immediately react with another equivalent of hydrogen and give us an alkane product. So with hydrogen and palladium on carbon as a catalyst, we'll always go all the way from the alkyne all the way to the alkane. What if we want to stop at the cis alkane? Fortunately, alkynes can be hydrogenated with a deactivated catalyst. This catalyst is called the Lindlar catalyst, and it's made up of palladium is the catalytic metal, adsorbed onto calcium carbonate, but the catalyst is poisoned with palladium acetate and quinoline. And so this reduces the activity of the catalyst, allowing the hydrogenation to be stopped after a single addition of hydrogen. So in this case, we start with the alkyne, we hydrogenate it over Lindlar catalyst to get only the cis alkene. What if we want the trans alkene, though? Yes, there's a way to do that too. In this case, it involves a dissolving metal reduction. In this reaction, we generate the alkene and we isolate the most stable alkene, which is usually the trans isomer. So what we see is we start with, again, our alkyne. Notice that there's no actual hydrogen gas used in the dissolving metal reduction. But our product has a net addition of 2 hydrogens, and notice that the 2 large groups here are on opposite sides, and so this is a more stable trans product. Let's take a look at the mechanism of the dissolving metal reduction, because this is a pretty interesting reaction. It involves 2 types of steps. One is a single electron reduction, and the second part is acid-base chemistry. So the way that this reaction starts out is considering that we're using sodium, and this is sodium metal, in liquid ammonia as the solvent. So remember that sodium has a single valence electron. And the first step of the dissolving metal reduction is that sodium to donate an electron to the alkyne. So we're going to draw it like this. It's going to donate one electron, so we use a single-sided arrow. It's going to combine with one of the electrons of one of the pi bonds. The other electron of the pi bond will go to the other carbon. So this is really a reduction step of the double bond of the pi bond. So we end up with a radical there and two electrons over here, so this is an anion. So we call this a radical anion. So what's the other byproduct of this step? Well, the sodium metal gives up an electron, and so it gets converted to the sodium cation. So notice that the pi bond accepts an electron, so that's being reduced. The sodium goes from sodium metal to sodium +1, so that's being oxidized. Now the radical position is neutral, but the anionic position is very basic. So it can react with ammonia in an acid-base reaction. This gives us this vinyl radical. Vinyl, remember, means it's on a double bond. All right, and so this is just an acid-base step. Now we repeat it all again. Sodium donates another electron to that radical. So we combine these two together, gives us off another sodium plus, and this vinyl anion. In this case, the vinyl anion orients itself so the two bigger methyl groups are opposite one another, so this is more stable. In the final step, we have another acid-base reaction. So the vinyl anion is very basic. It can pull off a proton off of ammonia, and that gives us our product, the trans alkene. All right. The other byproduct here is the NH2 minus. Remember, we've seen this as a very strong base that we used, in fact, to deprotonate alkynes. So we have a mixture of reduction steps. This step is really a reduction here. We have an acid-base step. We have another reduction, and when I say reduction, I mean of the organic part, and we have another acid-base. Okay, this always gives us the most stable alkene, which is usually the trans product as we see here. As a summary, we have a lot of control over the reduction of alkynes. We can either use hydrogen over palladium on carbon to reduce the alkyne all the way to the alkane. Or we can make the cis-alkene using hydrogenation with Lindlar catalyst, or the trans-alkene using the dissolving metal reduction.